This is a second lecture follow-up video from the first one released some 2 weeks ago. If you have not watched it, you might lose some context. I advise you to visit the channel and watch it first. I've upgraded my energy dashboard and I would like to take you through it before we go deep into the energy optimization. First, on the gauge chart, we have the total current power consumption for the house, which is 1.01 kilowatts, which is the sum of all the appliances that are working right now. Then we have the individual gauge charts for the actual appliances. You can see the pool pump is currently running and pulling 641 watts. Fridge also running, currently pulling 285 watts, and a few smaller components adding up to the 1.0 kilowatts total for the house. Then we have daily energy consumption bar chart for the 21 days of June 2021, which is around 40 kilowatt hours per day, i.e. some days are quite low, below 30 kilowatt hours, June 3rd, June 6th, and June 16th, and the worst day being June 9 at 47 kilowatt hours. It is very important to then dig deep and understand what was happening in both those good low days and the excessively high days. So the total cumulative kilowatt hours for the 21 days is 819 kilowatt hours, which basically is the addition of the 21 days kilowatt hours. If you do the rough maths, 40 times 21 is 800 kilowatt hours, so the maths adds up. Then this 819 kilowatt hour cumulative energy is converted into electricity bill so far by applying the effective electricity rate based on the three elements of the Eskom electricity bill discussed in the previous lecture. In my case, the consumption level, for my consumption level, it calculates to R1.90 per kilowatt hour. So the electricity bill for the 21 days of June is 1,560, which basically is 819 times 1.9. Again, the maths adds up. Basically, on the cumulative energy consumption of each appliances for the 21 days, we can see the breakdown of the 1.5K electricity bill for the major appliances, i.e. the big geyser is the biggest at 703 Rand, fridge, which includes a washing machine, at 230, smaller geyser at 187, and stove at 133. The lights are excluded, but they do add up to the total electricity bill. Then we have the chart of the last 24 hours, instantaneous power demand for the 7 major components, i.e. from 5 in the evening the previous day through the night and to date at 5 p.m. Throughout the night, the big geyser switches on and off for 10-minute intervals to maintain temperature. 8 o'clock, 10 o'clock, 1 o'clock, 4:30, 6:30, and 10. From 10 it ran continuously for an hour, replenishing the shower, and then continued with the 10-minute top-ups. Also notice that we had 2 power demand spikes that exceeded 7.5 kilowatt hours. That was at 6 o'clock the previous day and another at 3 p.m. on the day. Notice how the fridge, which is a yellow line in the evening, switches on and off in 20-minute cycles. Notice also how that the fridge motor starts. At times, it creates current spikes of around 10 times the current rating as it draws up to 2.5 kilowatts for that few seconds of startup. Firstly, as you might have noticed, I differentiate between power and energy. You draw power instantaneously, e.g. your geyser will pull 3 kilowatts, that's power. But when this power is drawn over a period of time, let's say 1 hour, it can be converted into energy. In this case, 3 kilowatt hours of energy. In other words, energy is the area under the raw power curve. The importance of converting power to energy is that the electricity bill is based on energy consumed in kilowatt hours rather than the power in kilowatts. But for industrial users, there is a penalty charge for maximum kilowatt power demand, as it is in fact the instantaneous power demand that causes load shedding, as Eskom has to deliver the power that is demanded instantaneously. So that hourly graph with the 2 spikes are very important to watch and drive down. My target is never to exceed 5 kilowatts at any one time by careful sequencing of components. In the next video, I'll go deeper and analyze what happens on days with low demand and those with high demand, so I can apply the lessons going forward. This point really is the beginning of the energy management and optimization program. We're gathering good historical data to use. An example, If you add the 10-minute cycles of the big geyser over a 24-hour period, they add up to 1.5 hours of effective continuous run. If you then add the 1 hour of continuous run, the total will be 2.5 hours for the 24-hour period. This will be compared with different scenarios where, for example, the geyser is on a timer. But judging at this, the geyser has excellent heat retaining properties with only 10 minutes required every 2 hours to maintain temperature. We will run scenarios where we will allow the geyser to lose all heat and only heat up to 3 hours before the shower time. Stay tuned for the next episode, which we will cover the geyser thermodynamics and impact of load shedding on energy demand.